The forces which kept this aluminium ball floating in space, and also those which caused it to spin, we call the forces of electromagnetic induction. Here in my laboratory at Imperial College, I'm surrounded by electric motors, all of which use this kind of force. The force is produced by electric currents in this coil, which induce further currents into this ball. So that this shows us at once that the only kinds of objects that we can suspend in this way are metal objects which are good conductors of electricity. Now, whilst it's reasonably easy to support a three-dimensional object such as a sphere, you have to be more careful with a flat plate. But it is possible to support a disc such as this one. Again, we have two coils, one inside the other, and this time each coil is wound on a laminated steel cylinder. When I switch on, we can suspend the disc, and if I now control the current in one of these coils, I can make the disc do different things. For example, I can make it oscillate, like that. Or I can make it steady again, floating higher up. Or I can tilt it over at an angle, such as that. And finally, eject it altogether. Now, each of these different actions could be said to be the result of an entirely different mechanism. Now, let me show you how we use induction forces in a different way. This time, we have a whole row of coils sunk in slots in a steel base, and they've been arranged in such a way as to propel this sheet of aluminium horizontally. Lay it on the surface and switch on. Once again. This time, without switching off, I'm going to put the aluminium back and hold it with finger and thumb at one end, so that you can see that as well as the horizontal force, there's also a lifting force. When I let go, of course, it shoots off. This is the force we designed it to have. The lifting force is something, in this case, we really didn't bargain for. Now, this is the linear induction motor. In many ways, it is easier to explain how the forces horizontally arise than is the case with the vertical forces or with the forces we saw supporting the sphere. But simpler still is a demonstration of induction using a single coil and a single ring, like this. Now, the ring is threaded over a steel core, which, as you see, is made up of a number of strips of steel. A bundle of iron wires will do just as well. When I switch on the alternating current, the ring is thrown in the air. Hold it down and release it, and it's again thrown in the air. But if I replace it whilst the current is still flowing, then it seems to float in the manner of the plate and the disc we saw earlier, and yet with this difference: it will never stay absolutely suspended in space. Now, let it go, it always has to lean on the pillar. Now, this is a very old experiment. It was first performed about 1880. But what was not realized until recently was this remarkable fact. If I hold alongside the steel core a copper cylinder, which is free to rotate, then nothing much happens until I put on the ring. That seems to spin the cylinder, and if I put the cylinder on the other side of the core, it spins in the opposite direction. It looks as if there was an upward sweeping something which is causing the cylinder to spin, as if it might be a current of air. Yet it can't be a current of air, because if I hold a feather duster alongside, the feathers don't move. Yet once we've established that there's an upward travelling something, we can make a pretty shrewd guess as to what it might be. It could be a magnetic field that is moving upwards. Now we can test this by mounting two magnets on a rotatable arm. The magnets are opposite this copper disc, which is also free to rotate. There's a good 1/4 of an inch clearance between the magnets and the disc, and yet when I rotate the magnets, the disc also spins. But it never quite catches up with the magnets. I don't know if this action reminds you of anything you've ever seen before, but if not, it might help if I turn the whole thing through 90 degrees and then try again. Because now it might remind you of stirring a cup of tea, in which the tea never quite catches up with the spoon. Thank you. Now the engineer needs little more in the way of explanation of an induction motor than this. As long as it reminds him of stirring a cup of tea and continues to give him right answers, he will continue to use it. So for example, he will see his linear induction motor as a magnetic river which is flowing along. And the fact that if I dip the cylinder into the river, you can imagine you could almost see the fluid flowing underneath the cylinder and causing it to spin. So from now on, we're going to think of our linear machine as producing a travelling series of waves of magnetic field. And when we want to design such machines, we need only study the mechanism of mechanical travelling waves. Now, waves in water are familiar to us. Most of us seen waves in the sea and ripples in bowls such as this, which I can produce by dropping in a small ball. But the mechanism of the waves is by no means obvious. What, for example, actually travels towards the edges of the bowl when I drop the ball in? Your first guess might be heaps of water. But do the heaps themselves really travel outwards? Let us test this by dropping the ball into a bowl which has some black oil poured onto the middle of it. If it's true that the waves themselves actually travel, then the sides of the bowl should become stained with oil as soon as the first ripples touch them. Let us try. And this obviously is not the case. Now we must examine this wave motion in more detail. And we're going to do it this time by means of a purely mechanical model. Each of these rods is free to move up and down, and they can only move up and down. I'm going to make them do such movement by means of a series of cams on a common shaft. When I turn the handle, something very interesting happens. Now this travelling wave pattern that moves along the top of this rod model is almost identical to the pattern of magnetic field which you get travelling over the surface of a linear induction motor. And in this stage, what travels horizontally is purely imaginary. To make it real, we have to add something else, like this. Now perhaps you think that it isn't obvious that what travels horizontally is imaginary without the ball. And so to convince you of this, I'm going to try to use the same model with a different set of rods. Now again, the tops of the rods produce the familiar travelling wave pattern. But suppose I take out every alternate rod. Will you then still be able to see the travelling wave? On this occasion, I think you would claim that you could, and that you would say that it was moving in the same direction as it was before. But suppose I take out every other again. Now, can you still say which way the wave is travelling? I think you'll agree that this is now much more difficult. And perhaps now you realize that what you were doing before was to join the tops of the rods mentally with an imaginary line, and it was only this line which was moving. Now we're going to go back in easy stages from this purely mechanical model to the linear induction motor. And the first step is to go from what is purely mechanical to what is electromechanical, like this. Instead of the rods, we're going to have a row of steel strips, and each of these strips is springy. Instead of moving them up and down with cams, we're going to use this row of electromagnets. When I switch alternating current into these magnets, it's going to cause the strips to be attracted and repelled alternately. And when I switch on the whole row, you should see a reproduction of our mechanical traveling wave along these strips. First of all, I'm going to magnetize the strips by passing direct current into this big coil at the back, which I switch on now. Now I switch on the alternating current. Now comes the second stage, in which we take away all the strips and place a track on top of the magnets. Built into this track is a steel strip whose purpose is to strengthen the magnetic field, and now I can place a slab of aluminium in at one end, switch on the alternating current, and we are back with our linear induction motor and our moving magnetic river. You can illustrate the difference between a linear induction motor and an ordinary electric motor if you draw poles on a piece of paper, like this. This, at the moment, represents a linear machine. But if I roll it up and make a cylinder, then the magnetic field moves round and round, and we've made our conventional household motor. But suppose I were to roll up the paper in a different way, like this. Now the magnetic field travels along the axis of the cylinder. We have made an electromagnetic gun. Now in practice, it's very easy to construct one of these guns, because all you need is a whole row of coils placed next to each other, like this. And each coil is simply a coil of wire wrapped on a bobbin. The moving part is going to be a steel rod with a copper sleeve on the outside of it. I put it into the barrel and switch on. The missile emerges at about 100 miles an hour and goes quite a long way into the wood. We can try more sophisticated darts. This one has alternate rings of steel and copper on a steel core. Let's see if this is any better. A little, if anything. A plain steel rod does remarkably well, because steel, remember, is a conductor of electricity as well as of magnetism. This tubular motor is not the most efficient of linear induction machines. I used it to show you another way in which you can use this amazing force of induction, which appears as almost artificial gravity under our control. Now, as an engineer, I must try and put this force to good use. And when I do, I must be sure that I'm getting the very best out of my machine. Now, one of the most advantageous arrangements appears to be to use two flat machines face to face, forming the outsides of a sandwich, with the aluminium sheet as the filling. Now, this motor is really a most potent device, but still pretty useless as a motor, because a fraction of a second after I've switched on and the aluminium has gone and we no longer have a motor. So if we want continuous motion, we must turn this machine over. Let this now be the moving part, and let it sit on a fixed rail and run along that, like this. Mary, would you like to give me a hand? Just take the weight until I can turn on the supply. Now I'm going to raise the voltage slowly, and the motor will climb this very steep incline. You'll notice that it doesn't need wheels to grip the rail. There are virtually no moving parts, and the motor is capable of developing a very large force. Taking off. I can control the motor for very low speeds. Or stop it when it's moving very fast. When used on the horizontal and made in a much larger size, such a machine is capable of developing a very high acceleration. At the Motor Industry Research Association laboratories at Nuneaton, the linear motor is being used to crash test all kinds of vehicles. This motorcycle will reach 30 miles an hour in a few yards. The victim for this test is a dummy, the same weight and size as a live rider. And when the bike hits a barrier at the end of the track, the effects of a genuine collision can be measured. The linear motor to do this job is very small. It's only about 3 times as big as our model which climbed the rail. Now it's being coupled to the carriage, and the final countdown is started. Interlocks operate on the doors, red lights flash, and once the final button is pressed, the forces of induction take over.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.